Welcome back. Let's get stuck into it and talk a bit more through another example to give you a sense of practice for how to pull apart regression estimates and interrogate a model. So the null hypothesis in a regression model comes down to an understanding of that slope, right? So we had the slope here before, and our null hypothesis is that the slope is equal to zero, right? So the beta, which is the slope of line of best fit, is equal to zero, and that here is the y-intercept is equal to zero. So unless the dependent variable is a ratio or meaningful zero, we're not usually very interested in the a value. So the starting value of y when x is equal to zero. We're only interested in that where it intercepts, where it cuts through that y-axis if the 0 point is meaningful, so typically in a ratio value. And so if that's the case, then the null hypothesis is that the intercept is equal to zero, and the null hypothesis for the slope is always that the slope is equal to zero. So that's what we're testing against when we see these significant values. So you may be saying, well, what is this significant value testing here? This is showing that the intercept is not equal to zero or different to zero. There's a significant difference. And similarly here, it's testing that adverts here, the slope is different to zero. So that's what those significant values relate to. Excellent. So here's another example, which is, does the speed at which one travels in a car predict the distance? This is actually stopping distance. So if you drive a car and you're driving at 50 kilometers an hour, what's that stopping distance? Is the speed at which you're driving, is that related to the amount of distance you travel when you stop? Because when you slam the brakes, the car does keep moving, right? So here's the distance on the y-axis, and on the x-axis we have the speed of the car, and you see the slope here, right? And so this is a data set that's available in R and base R. You could just call the car's data set. So if you go data equals car, if you just run this, it should populate for you with this data set or this output. And so what I want you to do is have a look at this output and have a go at trying to interpret it the best you can given everything you've learned so far in this lecture. So have a think, look at the output, pause the video, see what you can interpret, and then come back and we'll go together. So in this, we'll interpret it. So the ANOVA, right? That's the difference between the model here. So we have the line of best fit and the baseline model, which is just using the average distance. So it would have used the average stopping distance to predict it. And so when we look at that ANOVA, it shows, yeah, actually, there's a significant difference between these two models. So our model here, using speed and distance, it explains the variance in distance much better than just using the average of distance, right? So that's the key takeaway there. You may be asking what this one reflects. It actually is an option in R that allows you to let the intercept vary. So is the intercept free to vary? You can either set this as 1 or 0. If it's 0, the intercept must go through 0. But if it's 1, it's free to vary. So what that means if it's 0 is it would, this slope, it would change the slope to go through 0. Only if you have very strong theoretical rationale for doing so, you would force the intercept to go through 0, but most models, it allows the intercept to vary. So it looks at the data points, it fits it best as possible, and allows the intercept to go wherever it needs to go. And so that's just what that one reflects there. So the ANOVA is significant, and again, you're looking at here the ANOVA, and you're seeing actually it relates very closely to the F statistic here. So we have 89.567, 89.57, degrees of freedom, 48, the same, p-values are the same. So it's showing that our model, it explains the variance in distance much better than the average of distance alone, because our model models the speed as well that the car was traveling. Excellent. So that is that. The variance explained, you can see the multiple R squared is 0.65, so 65% of the variance is explained using this model, using speed to explain distance, stopping distance. And so that if we were to convert that to correlation, remembering the relationship between correlation and the coefficient determination, square root of R squared gives you 0.806. So that's the correlation between the two measures. So interpreting, so that's the model output, interpreting the output. Let's have a look at what it is in terms of the formula, so connecting the formula to the numbers that we see. So the intercept, hopefully you were thinking that's a weird intercept that's happening there. You see it's negative 17. So this is saying when the speed of car is 0, the distance is negative 17. And if you have a look here, you might get a sense as to why that's the case, right? I would imagine it's because this line of best fit, it extrapolates, right? So even though the values of the data go up to say 24, or 24 here, or maybe 25, it extrapolates beyond there, and it extrapolates beyond the point of the lowest value here, which is 3 or 4. And so that is important. So in this case, there's no data that was collected when the car was traveling 0. So it wouldn't make sense to interpret those extrapolations in this context. So that's why it's largely not meaningful in this context to interpret the intercept. But you still use the intercept because the slope fits everything else. So the slope fits your data points, but there's no real values when x is equal to 0 collected by your data set. If we had collected those values, this would be much more interpretable because the model would see actually, oh, okay, it's 0 when it's there. The 3.93 comes from here, so that's the slope, the speed of the slope here. So that's 3.93, that represents the slope that we see, and timesing by speed that's there. So in summary, linear regression is for explaining or predicting the linear relationship between two variables. We have y equals b of x plus a plus error, right? So the y is your dependent variable, your b is your slope, x is your independent variable, your a is where it cuts the y-axis, the y-intercept, and e is your error. And then here is where you have no error in your model. So if you have y hat, you have b of x plus a. So that has a perfect prediction in that second example. So let's now talk about multiple linear regression. So we talked about linear regression and correlation. Multiple linear regression is the linear relationship between two or more independent variables and a single dependent variable. So it's where instead of just looking at things in this context where you have speed and distance, you actually have multiple variables in that model. So it's two or more independent variables and a single dependent variable. So you can have a linear regression, which is just a single independent variable, single outcome variable, which is what we've looked at thus far. And then you can have multiple linear regressions where you have multiple predictors and your outcome measure. So what is multiple linear regression? It uses several independent variables to predict the dependent variable, and it weights each predictor according to the strength of its linear relationship with the dependent variable. And it makes adjustments for interrelationships among predictors. That's probably one of the most critical factors about multiple linear regression analyses. It actually adjusts your value based on the other variables you put into the model. So it provides a measure of overall fit as well, which we see with R. And so for variance, the correlation in simple linear regression, this is what we see, and this is what you're hopefully familiar with. You have variable A, variable B, and it's shared, right? This is in correlation and simple linear regression. It's what is the shared variance. Same idea in multiple linear regression, except that the shared variance is between multiple variables. So for correlation, partial correlation, multiple linear regression, you're saying what's the relationship between independent variable A and dependent variable B, and independent variable B and dependent variable B. So you have this sort of relationship here, and you can see the overarching loops that we see, A, B, and C. So independent variable A, independent variable B, and then your dependent variable here. Right? So that's really explaining that there's lots of shared variance between these variables, not only between your independent variables and your dependent variables, but also with one another. They can be related as well. So what are the steps to take when you run a multiple linear regression analysis? Well, actually, first, you think theoretically about the construct. So you develop a visual model, path, or Venn diagram, and state a research question and or hypothesis. So you might be asking yourself, you may be interested in, so a question that is common in my research area is what's the relationship between a risk factor and brain health? So it may be something like what's the relationship between sleep and brain health? And so you can model that relationship. But someone will say to you, okay, you say you see a relationship where there's actually some nuance, but it's typically people who sleep within a range are likely to have better brain health than those who don't sleep enough or those who sleep too much. That's really the a very simplistic overview of the research. And you may take that at face value, but or you may be interested in saying to yourself, well, actually, we know that age influences brain health. We know that as people get older, their brain can slowly reduce in size or reduce in functionality and in capacity or in whatever the outcome measure is, how quickly you can recall information. And so, how do you know this relationship that you see in this population is actually related to sleep versus age? And then you say, actually, no, this I've controlled for the effect of age. So I've actually added in age in the model. So this is the effect of sleep on brain health controlling for age. And someone says, oh, that's interesting. Well, how do you know that the relationship that you see isn't impacted by education? Because we know that there are relationships where people who have low levels of education have poor brain health and people who have higher levels of education. So how do you know actually all the variance isn't accounted for by the education instead of sleep? You say, well, actually, no, I accounted for education. I put education into that model as well. And so the estimate, the beta slope that we have here in terms of sleep and brain health is adjusted for these other factors, age, education, and you can go on, sex, whatnot. And so this is really the core of multiple linear regression analyses. You have these adjusted estimates. So it accounts for these other variables in the model. It controls for those variables. So you develop your visual model, and that's where that visual model comes into play. It's very theoretical. You're asking yourself, okay, I'm interested in sleep and brain health. What other variables could impact brain health? What other variables could impact sleep? What do I need to control for in my model? And that's where you state your research question, your hypothesis. You check your assumptions. You choose the type of multiple linear regression, which we'll talk about in a moment. And interpreting the output, we'll talk about an equation, develop a regression equation as well, which we've seen some examples of regression equations. So let's use a simple linear regression. 33.46% of variance in record sales could be explained by the amount of money spent on advertisements. Just to refresh your memory, that comes from our example here. So you can see the multiple R squared is 33.46%. So that's the amount of variance accounted for in our model. But you may be asking yourself, well, what about the other 66.54 of unexplained variance? Are there other predictors that may account for the variance in what sells a record or not? Maybe the number of times the album is played on the radio. And so we can ask and answer this question, but we first need to look through assumptions. So we have to look at level of measurement, sample size, normality, univariate, bivariate, multivariate, linearity, linear relations between independent variables and dependent variables, homoscedasticity, multi-collinearity. Independent variables are not overly correlated with one another, so not over 0.7, and residuals are normally distributed. You'll notice many of these are very similar to what we've done in correlations, what we've done in exploratory factor analysis, because they're all foundationally related to linear models or correlations. And I'll show you some of those links a bit later in the lecture as well. But that's why the assumptions are so similar across these different types of analyses. So let's talk through each of these assumptions in relation to this example question, which is we've explained the variance 33.46 of the variance in album sales to in relation to amount spent on advertisements. But are there other predictors that could add to the amount of variance that we explain in our models? So level of measurement is dependent variable is equal to continuous, so it's interval or ratio. The independent variable is continuous or dichotomous, the independent variable has to be either continuous or categorical. It could be dichotomous here as well. So if neither, you may need to recode into dichotomous variable or create dummy variables. In general, if your variable is continuous, you leave it. And recoding down to dichotomous variables loses information, and there's very rarely advantages to doing this. And so this is an important thing to remember when it comes to multiple linear regression analyses. And so, for example, you can put into the model something like sex for male and female into the model and look at the differences in males and females. So you dummy code them. So you may say males are 0, females are 1, and you're looking at the difference between the two. You could take another example of education, and you could have something like years of education, but you could also dummy code that into say categories of low education or high education. You have a threshold there. So in terms of recoding and why, often that recoding, you do lose information in the recoding, and so you should avoid it, but sometimes you gain interpretability. And so if that interpretability is there and allows you to say something meaningful about the measure, then you can do that. Otherwise, best to keep it as continuous where needed. And we'll come back to dummy coding. Sorry, I've gone ahead of myself. So dummy coding converts a complex variable into a series of dichotomous variables, 0, 1, because it needs to be dummy coded for the model to know what it is. In R, you can just put in the variable as is, and it'll take the first alphabetical level. So for example, if you have ethnicity and you say, or say country, and you have Australia, Europe, you have Africa, what it'll do is it'll actually go alphabetically through those, and it'll put the first alphabetical country first. So in that case, it's Africa. So it put Africa first and all the other countries there, and it compares to Africa. So you don't need to recode it, but you can. So you can assign a number, so 0, 1, 2, 3, and then you can compare to whatever the variable is. This is called dummy coding. So several dummy variables are created to represent a variable with a higher level of measurement. So you get a complex variable into a series of dichotomous variables. So that's dummy coding. So sample size, as always, there's guidelines around this. You just need enough data is needed to provide reliable estimates of correlations between variables. You can run multiple linear regression analyses with lower sample sizes. What happens is you have unstable estimates. You'll see that your standard error gets really large, and your confidence intervals are very large. Your estimates you lose a lot of precision and stability with your estimates. So if you want those stability and reliable estimates, you typically want more data. What are the guidelines? Well, a number is greater than 50 cases plus number greater than 10 to 20 cases times the number of independent variables. Otherwise, the estimates of the regression line are probably unstable and unlikely to be replicated if the study is repeated. So Green and Tabadak have suggestions, 50 plus 8 times k, so k is the number of variables you have, for testing an overall regression model, or 104 plus k when testing individual predictors, where k is number of independent variables you have, based on detecting a medium effect size, beta greater than 0.2, with the critical alpha less than 0.05, with power of 80%. So overall, there's another guideline of having 10 to 20 times as many observations as independent variables. So if you have 5 independent variables, you want at least 20 times that, so 100 observations to run a regression with those 5 variables. So really, those are the different guidelines. I'm just showing you what they are, so you have a good sense as to, is this assumption of sample size met? In reality, you calculate, in frequentist statistics, you calculate the power you need to detect effects, and you try to recruit the samples needed for that. And so keeping in mind sample size can be useful early on in the piece, not just when you have your data set available. So here's a practice question using these guidelines that you have. Does a researcher have enough data to conduct a multiple linear regression with 4 predictors and 200 cases? So they have 4 independent variables and 200 cases. The answer is yes. I'm assuming you paused the video because you saw a question coming. If not, I'm sorry for taking that win away from you. I'm sure you knew the answer too. So yes, because based on what we saw here, we have 50, so n is greater than 50 cases, plus 4 times 20, right? Because there's 4 variables, so that's 130 cases. The second example here, was n is greater than 50 in 8 times 4 cases, which is 82 cases, because it's this 50 plus 8 times k. And then in this example, n is greater than 104 plus the number of independent variables you have, which is 108 cases. So you can see these guidelines give you quite variable estimates. Largely, the more data you have, the better. But in this case, according to these guidelines, there's sufficient sample size to run the analyses. Okay, let's talk through outliers. So outliers are extreme cases that should be deleted or modified if they are overly influential. And what I really want to talk through is what it means to be an influential outlier. So univariate outliers detect out of range values via initial data screening. So you look at individual variable distributions and you see if there's variables that are outliers, so minimum and maximum values, and whether they're within the scale. That's if it's a incorrect entry. Say if your scale is meant to be on 0 to 5 or 0 to 7, you have values that are 9 or 10, you know that, oh, those are errors and those outliers should be removed. You can detect bivariate outliers via scatter plots, or multivariate outliers, which is an unusual combination of predictors, and you detect it via something called Mahalanobis distance while running an initial multiple linear regression. That's important to note, that for some of these assumptions, you actually have to run the model. You can't just check all the assumptions and then run your model. In some cases, you have to run your model and then check your assumptions as you go to make sure it's adequate. So let's talk about multivariate outliers. You may be asking, what does Mahalanobis distance do? Well, it actually statistically quantifies cases where a case may be within a normal range for each variable individually, but be a multivariate outlier because of an unusual combination of responses, which unduly influences multivariate test results. So, for example, say I'm doing a study on a population of people, of you guys, and I'm just trying to see the association between your backgrounds and, say, test scores, or your performance in this unit. And so I see how many of you are 18 years old. That may not be unusual, although I guess perhaps it is a univariate outlier. Maybe we'll take an example of university and scores, because this is a third-year course. But for example, a person who is 18 years old, it may not be unusual or detected as a univariate outlier in that case. If you have 3 children, it may not be a univariate outlier in that case of someone's coming to university. If you have a postgraduate degree, that's not a univariate outlier either in that case. But if you take all 3 together, someone who's 18 years old and has 3 children and has a postgraduate degree, then you're in a situation where that's very unplausible. And so that is likely to be a multivariate outlier. So it's the combination of multiple variables. Individually, they may be fine. When you add them together, it becomes something that is an outlier. So how do we check? Well, we use Mahalanobis distance, and that is distributed as chi-squared with degrees of freedom equal to the number of predictors. So with a critical alpha as 0.001. So cases with Mahalanobis distance greater than the critical value, 0.001, could be influential multivariate outliers. So you need to look at a chi-square table, and you look at 0.001, and you see how many predictors do I have? And then that's how we do, and we'll do that together in a second. Cook's distance is Cook's D. If you're, I don't know, if you like using shorthand, cases with Cook's distance values greater than 1 could be influential multivariate outliers. So this gives you a score for each of your observations, and it identifies those with a value greater than 1. So you want to examine cases with extreme Mahalanobis distance or Cook's distance scores. If in doubt, run analyses with and without and see if they influence the results. As you've heard from me time and time again, when it comes to outliers, you run your analyses with it, you run your analyses without it, you see if it unduly influences your results. Do the magnitude of effects change dramatically? Does something that was significant previously become non-significant, or vice versa? These are the things to keep in mind with your analyses. So for this level, in terms of this course, it's important to learn how to interpret Mahalanobis and Cook's distance. So the Mahalanobis and Cook's distance analyses will give the value for each participant. So think of this as how likely they are to be a multivariate outlier. So for every participant, you'll actually get a value for them. And the output will give the maximum Mahalanobis and Cook's distance, So Cook's distance should not be greater than 1. So there may be outliers if the maximum Cook's distance is above 1. So what I mean by that is you get your Cook's distance for each participant, and then if you look at the minimum, or more the maximum value, if you see the maximum is greater than 1, you know that somewhere in there in your data set you have some participants greater than 1, at least one participant. Mahalanobis distance should not be greater than the critical chi-square value with degrees of freedom equal to the number of predictors, with critical alpha equal to 0.001. So there may be outliers if the maximum Mahalanobis distance value is above this. You may be saying, what is going on here? Let me give you an example. This is a chi-square test. If you Google chi-square table, if you Google chi-square table, you'll find it there. If you were to set your critical value, the p-value here, as to 0.001, and say you have 4 predictors, that puts your Mahalanobis threshold at 18. And so when you run your analyses, your Mahalanobis distance, it shouldn't be above 8 your critical square chi-square value. So in that case, it would be 18 if you had 4 predictors. So it really depends on the number of predictors. So each analysis is different, depends on the number of predictors you have in that model. And you go to your chi-square table and you see, okay, I've got 2 predictors in my model, so the Mahalanobis distance is 13 at 0.001 threshold. If I've got 10 predictors, it's 29. So you can see how it increases with the number of predictors that you have. So that's Mahalanobis distance. Cook's distance is greater than 1. Those are the main takeaways. Why? Because they allow you to identify multivariate outliers, right? So that's the key takeaway from those 2 metrics. Let's talk about homoscedasticity and normality. So homoscedasticity is the variance around the regression line, should be the same throughout the distribution. So it's even spread in the residual plots. Normality, if variables are non-normal, this can create heteroscedasticity, right? If you have individual variables that are non-normal. And we've looked at examples as to what that looks like in the correlation lecture of where you have homoscedasticity and heteroscedasticity or nonlinear relationships is through the fitted and predicted plots that we can produce. So that is homoscedasticity and normality. You want the normality again to be related to your residuals, and so that's why in your when you run your analyses, it gives you these residuals here, so you can get a sense of, okay, are they normally distributed in your data set? Excellent. So that is that. The next one, I've done chi-square, multicollinearity. So this is the fact that in multiple regression analyses, you have your dependent variable and you have your independent variables. And the independent variables should not be overly correlated with one another. 0.7 can be an example, but the more important thing to take away is why. Well, it leads to imprecise regression coefficients because they're sort of taking the same share of the variance in the dependent variable. So if the independent variables are overly correlated, you can consider combining them into a single variable or removing one. And there's singularities that can occur. If you have perfect correlations among independent variables, then that they're essentially measuring the same thing. And that leads to very unstable regression coefficients. It does not mean that you should always do this. So multicollinearity, if there is a good theoretical rationale that the measures should exist in the model, and if the measures are sufficiently distinct from one another, they're not exactly the same thing or measuring the same thing. Maybe there's a lot of overlap, but there's a bit of nuance there. Then there's rationale for including it. But multicollinearity can cause an issue with your interpretation of estimates. So typically you want to check for it, you want to address it, but there's certainly research that shows that multicollinearity is something that needs to be informed, as with all statistics, through theoretical rationale of understanding your variables, your measures. Doesn't make sense to be included in the model. That should be the #1 driving thing when you're designing your multiple linear regression model. You're saying, do these variables make sense to be in here? Do they have some theoretical rationale motivating their inclusion? So collinearity is indicated by the correlation matrix. So if you have large correlations greater than 0.7 among independent variables, the tolerance factor is 0.3, or variance inflation factor is greater than 3. So these are just ways of identifying multicollinearity in your data. VIF, variance inflation factor, is the reciprocal of tolerance. So use tolerance or VIF, but not both. They're essentially the same, right? It's just reciprocal of one another. If collinearity is evident, reconsider the choice of independent variables if you don't have a sufficient theoretical rationale for their inclusion and you're having trouble interpreting the estimates. So what are the problems with multicollinearity? It's essentially what we see on the right here. So on the left here, you have your variables. They're sufficiently unique from one another, but they're explaining the shared variance in the dependent variable here in the purple. But here, when your two independent variables are highly related, they're essentially explaining similar amounts of the dependent variable, but they're also sharing variance very closely with one another. So are they measuring the same thing? And are they adding to the model's understanding of the dependent variable in the world? So that's essentially the core takeaway and issue with multicollinearity. So with restriction of range, you want to check the distribution, univariate descriptive statistics of your variables. And if you have restricted range, your correlations and regression coefficients are attenuated, right? So that can be an issue with your variables. One of the key criteria for a variable is that it needs to vary, right? So the variable has to have some level of variability within it. If you have a variable that does not vary, then like there's not enough people in different categories or distribution across the ranges, then it can be a challenge for your models, and also with restriction of range as well. So I mentioned briefly at the start of the lecture about causality, and I think it's worth mentioning again. Of course, in terms of science, the best method we have in methodology for determining causality is randomized control trials. You take people, randomly allocate them into different groups, assign some sort of intervention or treatment, and see what the effects are, because it sort of spreads that the contribution of other variables. It's random because of the random allocation. It addresses that. But in multiple linear regression analyses, like correlation regression, it does not tell us about the causal relationship between variables. But as I've alluded to already, it can if you have a theoretical rationale for the direction as to which way things are going. So in many analyses, the independent and dependent variable could be swapped around, and therefore it is important to adopt a theoretical position. You need to be able to say, theoretically, the direction of effect is more likely to go this way, but also acknowledge alternative explanations. In pretty much every paper I'm writing, when I'm discussing the effects, I'm always considering, well, what are the possible situations that would result in an alternative explanation for if the direction went the other way from the dependent variable that I've allocated to the independent variable. And so these are things that you have to discuss and keep in mind, but the method of multiple linear regression analyses can help with this thinking. This is where the statistics divide from the theory of regression. So interpreting multiple linear regression output, so you'll encounter some the big R capitalized, which is the multiple correlation coefficient. It's actually the equivalent of your Pearson's R that you're familiar with, but it actually takes into account multiple predictors. So in multiple linear regression models, when you have multiple independent variables, you have your R squared, your coefficient of determination. So here it says 18%. And then your big R shows you the similar to the correlation coefficient between the key variables of interest. And it's always positive between 0 or 1. That's in multiple linear regression models. So yeah, big R squared, that's your coefficient of determination. It's square to the multiple correlation coefficient. You want to always report the R squared, how much variance in your model is accounted for by the model that you have, how much variance in the dependent variable or the residuals is accounted for. Indicates the percentage of variance in the dependent variables explained by combined effects of the independent variables. So it can increase or stay the same with the inclusion of more predictors. And it's analogous to little r squared here. And so you can see both, and they're pretty much the same thing. Now, this is the key point to keep in mind, that if you have a model that looks at, say, we'll keep with the example of number of records sold and albums, records sold and amount spent on advertising. If I created a model and I added just 10 more covariates into that model, it can actually inflate R squared artificially just by the nature of having a lot of covariates in the model. And so there's something called, I'll come back to this, there's something called adjusted R squared. So R squared is the explained variance in the sample. Adjusted R squared is the explained variance in the population. And it's good to report both R squared and adjusted R squared, although I don't actually see adjusted R squared reported a lot in the literature. But it's important to take more note of adjusted R squared, particularly for small sample sizes and where results are to be generalized into the population level, but particularly when you have a model with lots of covariates, because that can inflate your R squared artificially. So if you see a big difference in adjusted R squared and R squared, then that's where it's important to report the adjusted R squared. The coefficient determination R squared, there are guidelines for the strength of relationships or amount of variance rather that's accounted for by your multiple R squared. So in 0, it's no linear relationship. 0.1, it's small. 0.25 is moderate. 0.5 is strong. 1 is perfect linear relationship and amount of variance accounted for. R squared greater than 0.3 is pretty good in social science. What you want to be seeing is if there's anything that's really small, like less than 0.1, you want to be interrogating the question as to what other variables could account for the variance in our dependent variable, and have we measured it? Could it be investigated? These are the key things to look at. So the overall significance of multiple linear regression model tests whether there's a significant linear relationship between all the x variables and y, right? So we have multiple variables in our model, and we're saying, is there a relationship between all those x variables and y, indicated by f and p values in the ANOVA table, and p is the likelihood that the explained variance of y could have occurred by chance. So that's the key takeaway in terms of significance of multiple linear regression models. I think a key thing to take away as well is when we run these models, the choice again is the choice as to which independent variable we're interested in is theoretical. So for example, do we have an example? I think there's another example we'll be doing in a moment in relation to album sales, but let's take an example of brain health outcomes, and we'll continue with sleep and education and sex, and we'll leave there for an age, for example. Now, the question looks at what's the relationship between sleep and brain health, right? And it looks at that relationship, and we've controlled for all these factors. So then the interpretation is this is the relationship between sleep and brain health, controlling for age, education, sex. Now, if I was to look at the relationship between age and brain health, it's the same model, just controlling for education, sex, and sleep, right? So that's the same model that's occurring there. So the choice as to what we choose as our independent variable of interest and what we're controlling for, in some ways, is theoretical. The model procedurally can be the same, and you just change which independent variable is the focus, and it controls for all others. So that's the overall significance of multiple linear regression models and the each individual's one. Yeah, so indicated by P and F values in the ANOVA table, which you see, and P is the likelihood that the explained variance in Y could have occurred by chance. So this is a multiple linear regression equation. Hopefully it's becoming more familiar to you because it just extends on the simple linear regression model with multiple variables, right? So you have B2, B3, B4, all the way, and so BI represents infinite number of variables you can include. And so Y is the observed dependent variable score. BI is the unstandardized regression coefficient, slope x1 to xi, however many, 10 or 12 or 5 independent variable scores. A is the same as before. It's where it intersects the y-axis intercept. And E is the error, so the residual error that you see in your model. So that's the multiple linear regression model, whereas the normal regression model that we had did not have this B2 to BI. It was just B with your y-intercept and the error. So again, the y-intercept is A, so A is where the x crosses the line crosses the y-axis when x is equal to 0. Slope is B, so this is unstandardized slope, and slopes are the weighted loading of each independent variable on the dependent variable adjusted for the other independent variables in the model. So if you put 5 variables into your model, you will get a slope for each of them. And the interpretation is this is the relationship of this variable, this independent variable to the dependent variable, controlling for all the other ones. And then if you look at this slope for the variable 3, that's the relationship between variable 3 and y, controlling for all the other variables. So that's what the slopes are when you get an output in multiple linear regression. So the unstandardized beta coefficients, beta is equal to the unstandardized regression coefficient. It's used for regression equations, used for predicting y-scores, but cannot be compared with other betas because they're all on different scales. So age, the beta or slope for age cannot be compared with the beta or slope for sex or beta or slope for education unless I convert them all into standardized betas. And so then they're measured on the same scale. So when we looked at that standardized example before, again, if we have multiple variables, then that we can also start comparing the size of effects between them. We could actually say for brain health, age has the largest effect, followed by sex, followed by education. So we can actually quantify the difference between those measures. Sorry, standardized regression coefficient, that's what this is. So you have the B, and then here you have beta, standardized regression coefficient. It's useful for comparing relative strength of predictors. So beta is equal to R in simple linear regression, but this is only true in multiple linear regression where there is one independent variable, where the independent variables are completely uncorrelated, which is very, very rare. So if there is one independent variable in the multiple linear regression, it's essentially a simple linear regression. And so that's why, as we've seen before in the correlation lecture, a simple linear regression is the same output as correlations. They're all related, interrelated concepts. What's the significance of independent variables? So it indicates the likelihood of a linear relationship between your independent variable and y, your dependent variable. What's the likelihood that it occurs by chance? So the hypothesis, the null hypothesis, is that the slope is equal to 0, so there's no linear relationship. And then the alternative hypothesis is that there's some direction there, so the linear relationship between your independent variable xi and your dependent variable. So relative importance of independent variable, which independent variables are the most important? To answer this sort of question, you need to standardize all your regression coefficients. So if you just put them in your model, they're unstandardized. That's in their unstandardized means they're in their regular units of measurement. Standardized is that's the interpretation of saying for one standard deviation change in X, we see however many standard deviation change in Y. That allows you to compare across different measures. So here's the example does the amount of money spent on advertisements in the week before the release of the album in thousands of dollars. For example, adverts, the number of times the song is played on the radio in the week before the release of the album, which is airplay, and the attractiveness of the band members. So attractiveness on a scale of 0, low levels of attractiveness, to 10, high levels of attractiveness, predict the number of record sales in the week after the release of the album. So we have 3 key variables: airplay, attractiveness, and adverts spent on the advertising. Do they predict the number of sales that are there? That's the example. So here is what that looks like in the model. So we have sales as our dependent variable. We have adverts, airplay, and attractiveness in this data set. Here's our residuals. We can see they're pretty much close around 0 and relatively normally distributed. You can see that by these numbers are pretty similar to one another. Although this is a bit larger, but largely it's normally distributed. We have our intercept. So when x equals 0 for all of these things, y cuts the intercept at -2.6. And this is in unstandardized values. This is in standardized values, right? So we have our standardized units here, standard error, and the t-value that's here. So in unstandardized beta estimate, we have the sales is equal to beta 0 plus beta 1 of advertising. So beta 0 is -26.61. So that's the intercept here, times 0.08 times advertising, times plus 3.37 times the airplay, plus 11 times attractiveness, right? So that's the interpretation of how the model looks based off of sales. And so those are the key takeaways there. You can see, looking at the standardized units here, that we have differences here, right? We can see that adverts in fact, and airplay are probably the biggest predictors of album sales compared to attractiveness of the band members. But it does seem like attractiveness of band members does have an impact on the amount of records sold, but it's not as big as the adverts and airplays, right? And adverts and airplays are somewhat comparable. The whole point of this is to show you that standardized column allows you to make that interpretation. You couldn't say that with this unstandardized column. Now, something I want you to keep in mind is what I said before in terms of the estimate divided by the standard error gives you the t value. The t value is actually in some ways standardized. So if you look at these values that you see here, you can already see that it's 12 and 12 and then 4. These match on to the relative weights of here, so 0.5, 0.5, and 0.19. And so you can actually also look at the t-values to get a sense of the weight of the different predictors. But you can also use standardized to get a more interpretable estimate, because then with these values, you can say for every 1 standard deviation increase in adverts, there's a 0.51 standard deviation increase in sales after controlling for airplay and attractiveness. Similarly, for every 1 standard deviation in attractiveness, there's a 0.19 increase in sales after controlling for airplay and adverts. It's really key because all of these estimates are accounting for the other ones included in the model. Each of these estimates account for each other. They're controlling for the other estimates in the model. So that's the key takeaway there in that example. And so what we'll do is, before we go, so that's a multiple linear regression model in action. We'll take a break, and when we come back, we'll talk about the different types of multiple linear regressions that are out there. So take a break, stretch your legs, you deserve a tea, deserve a coffee, have a good reflection on what you've learned, and then we'll come back into the next section.